let's do the digital logic test question, which involved reading a number from a 7-cell display rather than sending one to it. In part A, we're asked for the truth table for a NAND gate. NAND is negated AND, so we want a 1 exactly if they're not both true, so 1, 1, 1, and then here they are both true, so we have 0. That's the truth table for a NAND gate. And then we are asked to construct not and an or using NAND gates. Well, not is given by tying NAND legs together, so we're using either the top row or the bottom row of the truth table, and takes a negated and uses not to negate it back, and then or, well, we take a NAND gate, and this tells us when things are not both true, and or will tell us when they're not both false. That means we need to negate the inputs. So that's our useful components, not and or, built from NAND gates. Now back to the 7-cell display. The following diagram shows the plan for a 7-cell display, but this time the 7 signals, A, B, C, D, E, F, and G, are the inputs, and we have to recognize when one of these 4 patterns is being displayed. A helpful friend suggests that cells A, D, and E should provide enough information to identify which number is being displayed, assuming that what is being displayed is one of these 4 numbers. Not all combinations of A, D, and E conform to a valid number pattern, so give the truth table for a signal V, which is 1 exactly when A, D, and E do conform to one of the 4 valid patterns, and identify which pattern it is by filling in 2s and 1s in the rows where V is 1. Okay, so that's to say we're taking A, D, and E as inputs for a truth table, and then we have an output V for whether or not we have a valid number, and 2s and 1s for which number it is, just in the case where V indicates that we do have a valid number. Let's tabulate all possible inputs in increasing order. Okay, and now let's go and look at the diagrams to see whether we have any matches. Okay, so in the case where A, D, and E are all switched off, well, 0 has A switched on, so that won't do. 1 has A, D, and E all switched off. You can see that 2 and 3 both have A and D switched on. So it does match a valid number, and that valid number is 1. So let's fill in a 1 here to say that this combination gives a valid number, and the binary code for 1 to say which number. Okay, how about this combination? Here A and D are both switched off, but E is switched on. Are there any patterns which have A and D switched off, but E switched on? Well, 3 of them have A switched on, so they're ruled out, and the other one certainly doesn't have E switched on, so this combination of inputs does not give us a valid number. And the same reasoning rules out A switched off, but E switched on. Again, there's only one candidate, that's not valid either. How about this combination? Only D switched on, A and E switched off. Well, if we look at the ones where D is switched on, we see A is also switched on. So this isn't a valid combination either. How about if A is switched on and D and E are both switched off, then what have you? Well, here A is on and D is off, but E is on. So close, but not quite. Here A is off, and in these two, A and D are both on. So again, this combination isn't a valid number. What about the other three? We've only got 3 left, and we've got 3 numbers still to find. So let's hope our luck improves rapidly. If we have A switched on and E switched on, but no D, well, we better be looking over here. Here we have A switched on and E switched on, but no D. So yes, it is a valid number. It's the number 0. So we fill in 1 for valid, and then the binary for 0 in the 2's and 1's column. How about this? A and D, but no E. Well, let's look. Here are 2 combinations that have A and D, and this one, 3, has no E. So this is a valid combination, 1, 1, 0, and it corresponds to the number 3. This is 3 in binary. And finally, the combination where A, D, and E are all switched on matches number 2, A, D, and E. So again, it's a valid number, and the number that it represents is 2. Okay, so for the remainder of the question, we have to build a circuit using NAND gates, which first of all delivers V, and then in the case where V is 1, we have to explain how to compute 2's and 1's. So how will we build our circuit to implement V properly? Well, we might as well not try much harder than to use the standard way to implement a circuit when we know the truth table, namely to exploit the fact that the truth table gives us an easy disjunctive normal form. We certainly have not and an or at our disposal, so let's get cracking. What do we need to do? We need to consider the cases where we get a 1 in the output. That's this case and these 3. We can save ourselves a little bit of work by noticing that if A and D are both true, then we don't really care about E, but otherwise we'll have to consider these 2 cases separately. Okay, so we'll have or wired up to V, and then another or for each of the cases we care about. We've already said that we want an and here, and these are going to be A and E. And now what are our other 2 cases that we have to build detectors for? They are 0, 0, 0, and 1, 0, 1. So we turn the zeros into knots. And then we AND everything up. Better connect. I'll just write the names of the signals A, D, E, A, D, E, and these were A and D. And we've built our circuit for computing V. Now to finish the job, we need to build circuits to compute 2's and 1's, but they need only give the right answer in the cases where V gives 1. And we can see from this truth table that in those cases, 2's is always a copy of D. So we can wire D's, we can 2s down to, no, we can wire 2s directly from D. Similarly, if we look at the 1's output, we can see that 1's is always the negation of E. So we can get from E to 1's with a NOT gate, if we're managing not to be silly. So we've built the circuits for V and 2's and 1's that detect, we hope, when the 7-cell display is showing us a number, at least as far as we can tell from signals A, D, and E. That's the question finished.